Just to let you know, in this session we'll be talking about diesel engines. If that's not what you want to hear about, you might want to go find another one. It's not a sexy topic, but that's what we're going to be talking about today. Diesel engines, the policies, the regulations, documentation that goes, the selection of them. It's across the years, it's become much more complex and important with fuel cost rising, and the EPA and DEC regulations become much more important. And again, especially since about 90% of rural energy is generated from diesel, it's probably one of the most critical decisions you can make for your powerhouse, the selection of your engine and to stay in compliance with the EPA regulations and documenting that. And we have some pretty experienced guests. I'll start with a little bit of housekeeping I was told to inform you about. There's a survey form. I don't have one up here, but out on the front desk up there, if you'd fill out that survey form about this presentation and give your feedback, that helps us in the next presentation. We do have some continuing education forms. If you want one for the engineers out there, come see me. You can get, I think it's about an hour and a half worth of CEU for these presentations. Come see me and we can fill that out and get that signed for you. The last housekeeping, there are 2 lunches today, 2 areas for lunch. One is right around the corner here in this room where the breakfast or snacks were served, and the other is over in the Northern Latitudes restaurant. So the actual restaurant will be where you can go to get lunch inside the Northern Latitudes. Again, 2 places, your choice, in the room adjacent to this conference room or in Northern Latitudes. Before we get started, I'd like to kind of give you a little bit of background on each one of the speakers. Scott is the general manager, and Scott Newlun, who's right here, he'll be first. He's the general manager for the city and borough of Yakutat for the Powerhouse, and he has a very interesting story on his Powerhouse. That's kind of why we brought him in here. He learned about the EPA regulations and the policies the hard way, and it just happened upon him, and he'll give you that experience, and then we'll follow it up. Brian Gray here in the John Deere shirt, the bright yellow John Deere shirt, will be presenting to you next. And Brian has about 25 years of engineering experience. His primary emphasis in his engineering is rural Alaska. So he has, again, a considerable experience in rural Alaska, heat recovery, diesel engines, a lot of this off-grid power. And then Steve will follow him with more discussion on regulations, engine selection, the documentation that's required for these powerhouses to comply with the regulations. Steve's got about, again, 25 years of experience, and he's been involved in more than 125 rural communities in engineering projects for them. So are there any questions in general first that we can start off with? What we'll kind of try to do is, as the speakers are presenting, you can feel free to raise your hand during his presentation. If we get too many questions, I'll have to limit it so we can continue on. But if you have a question while they're presenting, raise your hand. They'll call on you. Again, if we have a few too many questions, we'll have to limit them and move on. We'll try to give you a time after each presenter to ask questions, and then a time at the very end to ask any of the presenters questions. So without any further, Scott Newlun, the city manager of Yakutat.
Thanks. Hello, everyone. You know, one of the most important decisions we make when we put these plants together is what type of engine to get and how efficient they're going to be, et cetera, how we can permit them. So I'll tell you a little story about when we decided that we needed a new power plant and to change our lineup, how we went about that. One of the first things we did was try to look for the most efficient and reliable engines that we could find, okay? The first step in that for us was to contact the AEA and ask for their assistance, and with that, we got the help of Gray and Stassel Engineering to help us size these units after we'd already purchased a couple of them. You know, we had an old plant and we started replacing the engines pretty early on. I think in 2000 we changed 2 of our engines out to 3500B series, a 3512 and a 3508. And we installed them and liked their efficiency and their reliability. So we decided next we were going to go with a new 3516. That was our next step that would help our lineup and have a good redundancy scheme for our new plant. So we went ahead and started the process and started researching. We knew that the Rice knee shaft and the NSPS ruling was going to change. We weren't sure of the date. They hadn't announced it yet for the air quality permitting. So we tried to make sure we got way ahead of the curve. We researched it a little bit with NC Caterpillar and picked out the unit we wanted. We got an aftercooler circuit built into it so we could have better efficiency. We also purchased a very good Cato generator for it because we knew this would be our main engine that we use for years to come. So we ordered it in the end of 2005 and got it in the lineup. Do I have to hit something? Okay. Okay, anyway, this is our lineup in our old Powerhouse. So we purchased the new engine, got it set up, and started operating it, and we were very happy with its performance and its efficiency. So we were pushing around 15 kilowatt hours a gallon on our fuel efficiency, and that's what we strive for, is about 15 kilowatt hours per gallon of fuel. Well, we had the 3 engines purchased. We built the new plant, 2011, moved our engines over there, purchased another 3516B, and made sure it was a pre-2006 scheme. And as soon as we got them set up and started to run them, we had an inspection from the DEC and the EPA. They came through and read all the serial numbers, went through everything, because we were updating our air quality permit. So we had to change a lot of the lineup and the technicalities about it. So they came in and actually went through each machine and they read all of the serial numbers, cross-checked them, etc. And they came back with a ruling that our new engine that we'd purchased had been built 2 months too late. And we started the conversation of how are we going to get this thing permitted. We were ahead of the scheme, tried to get it manufactured on time, and now we were up against the issues of the law had changed, and it was our burden to prove that this machine had fallen into the Rice knee shaft air quality permitting. Well, the process began, and this is a copy of the notice of violation for operating this engine. The process began, and we started to contact the manufacturer, call the plant, Peoria, trying to come up with an idea of how we could prove that this machine was legal with the air quality scheme. So we could never do it. Caterpillar couldn't produce the born on date for us, etc. So anyway, we kept operating the engine until we could come up with a resolution, and we're working with the DEC and the EPA all along this way. They issued this notice of violation, and this was about a year later. We said, what do you want us to do to try to solve this? They gave us a couple of scenarios of what we could do. But in order to become compliant, we had to take a 10% fuel penalty, which put this engine out of the realm of operation for us. It would cost us about $100,000 to $200,000 a year if we ran that engine with a different profile programming on it. Okay? So we kept running it for a while. Got this notice, and if you notice the second to last paragraph, it got pretty serious. You know, and then we started really standing up and listening and trying to find a solution to it. So eventually, I got the word that I was the person responsible for it, and I was subject to these civil fines and lawsuits that were to follow if we kept operating it. So we shut the engine down and locked it out, needless to say. That would have put a pretty big damper in my wages if I had that fine. So then we contacted attorneys and a consultant to help us try to work through this program along with EPA and DEC. And there were a couple of schemes we could do. The one was to reprogram it to try to get it in compliance with a Tier 1 level, which gave us the fuel penalty. And Caterpillar could do that with a new program. So we go, wow, we really don't want to do that. So we researched and researched, tried to find an answer. And one of the other issues was we could come in and do a full source test and prove that the pollutants weren't as bad as what they said they were. But when we researched that, that was $20,000 to $30,000 to mobilize a full source emissions test. So we argued with them a little bit, tried to come up with a solution that would let us keep that profile and the efficiency for the engine because the community couldn't afford to pay that much for fuel. And then we ended up getting a compliance order by consent, which laid out what we had to do basically. And if we had to operate that engine in an emergency, we could notify them and they would make a ruling on it. Well, that scenario happened a few months later, and we had to run that engine to keep the processing plants going, et cetera, because some of our other engines failed. So we ran it, documented it, contacted them, and we're waiting for the variance. Never really heard anything back from them, so we shut it off, and we were still negotiating, trying to come up with a solution for it. After several attempts working with these guys, trying to come up with a solution, the EPA and the DEC, we finally issued a case of why we thought we should be able to use it and what our plans were to fix the project. So basically, I'd offered up an opinion of what we could do. Send it to the EPA, DEC, let them look through it and come up with a ruling, say yes or no. And we ended up bringing in NC and reflashing the machine to a different program profile, taking the 10% fuel economy penalty, and that's how it is right now. So we did that, got all the certifications, all the technical paperwork ready for them, presented it to them, and they released the citation. So now we have a great emergency standby generator that's sitting there. I mean, we can still run it. It's about a kilowatt hour per gallon less than our other units, but it's in our lineup for redundancy, so we have a safety factor in place. We're still trying to find out a solution to the problem. We're looking at dual fuel capabilities, maybe putting some natural gas in it and cleaning up the emissions, et cetera, and get our efficiencies back up. But right now we have such a big investment in this engine, we have to keep it in the lineup, and we're in a little bit of a quagmire of what to do. You know, as we go down, if there's no solution, we'll have to replace that engine and that genset and try to come up with something that's as efficient as our other plants. But in this age of air quality regulations, it's hard to find that efficiency to meet the air quality that we have. So it's worth the time to try to come up with a solution for this and get back up to the 15 kilowatt hours a gallon. It just makes sense in the long run when you pencil out the fuel savings and the costs involved. So in the meantime, we're going to keep running our diesel plant and try to be as efficient as we can. And this is a shot of the plant and some of the local grade school kids that come by and tour, et cetera. And that's basically the end of my presentation, but I wanted to stress that, you know, even in remote Alaska, and you think you're doing all the right things, and you go through the process, spend the time, do the diligence, things can happen. And there's regulations out there that can't be breached. I mean, the EPA and the DEC were great to work with. All the people there were great, helpful, didn't fine us, let us get away with more than most people would have. And they still had to follow the rules. And that's where we ended up with it. And right now, we still have that engine in the lineup. We use it occasionally. And lesson learned. You know, that's what we thought, that we were ahead of everything, but some things slipped through the crack and we still got caught with it. And that's it. Any questions? Yes?
So I'm wondering if some sort of multi-stage sounds accurate.
Well, when we looked into treating the emissions, there's a cost involved in that also, and it offset the fuel penalty to have the urea injection, et cetera. So, you know, we'd have looked at those issues. We've looked at fuel additives to knock down the emissions, et cetera, but you still have to do the full source test if you use those. And we're still looking at some other schemes. Like I said, the dual fuel, some of the additives still show some promise. There's some new technology that might come out in the exhaust streams that's not as cost intensive. And we'll retrofit if we can. Mm-hmm.
How much natural gas is needed for the
Well, it's yet to be determined. You know, it's a formula. We burn approximately 500,000 gallons of fuel a year, diesel fuel. So it's easily obtainable, but, you know, we're looking at a dual fuel system because we could have the redundancy of going either way with it, and you can offset up to 70% with the gas. But right now, the infrastructure isn't in place for the liquefied natural gas to be shipped up and down the coast. Thanks.
So this is because you have a Title V permit. Is that right? Or will this also for the environment?
If you repeat the question.
Okay, he asked if it was a Title V air quality permit, and we were operating off of a general permit, and it still got picked up. And the difference between the Title V and the general permit is a general permit is a lot less intensive on record keeping. Title V for larger operations is a lot more intensive.
I believe they don't, the Yakutat not required to have a Title V under 850,000 gallons a year. So they fall into what's called the general permit A or DCA category. There's about half a dozen of these
I guess my concern was, does the date matter if you have
Yes, yes, it did.
We'll get into that. It'll be in Steve's presentation.
Yeah, that'll be later on, but these guys will get into more detail with it because they were involved along the line with the sizing, the engine selection, et cetera. Steve was a consultant that we had working on this case, so he has some good answers to the questions. But, you know, what it did to me was open my eyes saying things can happen when you don't expect it. And then you have to either live with it or come up with a solution to it. Okay? Thank you. Oh, yes, when the load dictates it, we will parallel smaller engines. We have a 3508, a 3512, and two 3516s. Right, right. Okay. One more.
Mark Thompson with Notes Power. We make presentations. We produce variables. So I guess my question is, we're seeing, when we do evaluations of different data, we never see this back but I didn't really realize how rigorous the restrictions that have made in Alaska emissions because of the environmental diesel. We don't know how the driver is yet. So that is the environmental side of it. I don't really know this data static.
No. Can you comment on that, Steve?
I think your underlying question is what's the status of environmental regulations, air quality, and
Yeah, we're under the impression that it's pretty stable, that people get accepted, unrestricted infrastructure. It sounds like that's not the case.
Right. My presentation will talk a little bit about
Okay,
that.
let's move on.
But the regulations are in place. There's new regulations that are being challenged right now, trying to come up with a variance for the state of Alaska. Because what happens is as the air quality emission standards rise, the efficiencies drop. So, you know, in my opinion, we get a net gain of zero. We burn more fuel to produce more electricity, but with less emissions. But over time, you're still sending a certain amount of pollutants into the air. Okay?
Hey,
Thank you.
Scott, I got a couple questions
Oh,
for you.
okay.
Just
Go ahead.
to set the stage, and by the way, there's a mic here for questions. I was trying to get it out there, but I didn't. Is it, maybe you can describe to me, I believe this engine, this last engine that you just discussed, was ordered, we thought, in time,
Right.
but it got delayed because
Right.
the receipt of the engine to the Powerhouse got delayed. Is that correct? Beyond your
Right.
control?
Actually, the manufacturing did. So we tried to be ahead of the curve. We knew the changes were coming. I don't think the EPA had published the exact dates yet. So end of 2005, we put our order in, made sure we made the down payment, et cetera. Well, there was a little thing called Hurricane Katrina, and a tsunami happened in that time period. And it set the production back. So that was one of the issues with it. So when we went to the manufacturer and started trying to put the burden on them, they had a way out with it.
So is this engine not, besides the serial number and the date it was manufactured? Do you have is there another engine in your plant that's exactly like this one that is compliant?
Well, there's
Is
another,
that the correct statement?
the correct statement is there's a pre-2006 3516B that we purchased when we built the plant that is compliant. But this one was a born on date several months too late.
So I'm trying to establish for the audience here, the only difference between the two engines is the born date, the
Right.
date it was manufactured.
Right, and the
two
born
engines are
date-
identical in the plant, $750,000 investment, two identical engines in the plant, and the only difference is the date it was manufactured. That's it. Two identical, and he can run one, but he can't run the other.
Right, and they were very rigid with the date. And the born on date was the day they laid the crank into the block. And that's what they wanted to see.
And if I recall, it was about 3 months after the April 1 deadline.
Right, and the April 1 deadline was established, I think, in December of that year.
Right. So it was a timing issue. You know, everything, it was ordered in time. Construction, fabrication was delayed extensively because of Hurricane Katrina and other environmental catastrophes. And so nobody, I don't think, realized that when the unit was finally delivered that magic date had passed. And it was all during the time frame that it's the New Source Performance Standard rules. They were published in July of 2006, but they weren't formally adopted until a year later. And so all of this was overlaying itself. And even the EPA and DEC didn't realize it for 3.5 years.
Right, and we operated it under a new permit for 3.5 years. So those are some of the challenges that you face out there as you size new engines, and it's going to be there. So you have to be aware of all of the nuances that go with sizing up new engines for your power plants.
Thank you, Scott.
Thank you. With that, I'd like to introduce Brian Gray.
Open disclaimer, I don't have any preference in brands of diesel engines, so just booting up our slideshow here. Scott is a unique example right now in the state of Alaska, and I think if he had his druthers, he would rather have not been that unique example. But, a lot of times we think, well, I'm off the road system, I'm in Bush, Alaska. Who really cares what they say in Washington, D.C., And then the day you get a letter that starts talking about $200,000 fines, suddenly it matters to me, And so, the two things I think we have to really keep in mind is these are very serious regulations, and pretending like they don't exist is not an option for us. And they're very complex, and you have to really think and thread the needle through it. Most of the people that are actually charged with enforcing these regulations understand parts of it, but not the whole of it, and it's very complex to try to understand it all. So, it's a reality that we now live in. So, on that kind of sour story, I'm going to just give us a happy moment and take us back maybe into the good old days. Around 2000, most of rural Alaska fuel was around $1 something a gallon. Fuel was pretty cheap. And diesel engines, by and large, are pretty simple and reliable. And you had these, foolish people that had a brand preference or whatever, but it was kind of a Ford Chevy thing. I mean, most diesel engines were basically the same, and they were pretty reliable. And it was very common for most of these engines to go even up to close to 20,000 hours between major rebuilds, and without a whole lot of problem. A water pump would go bad, maybe a fuel pump, or change some injectors, but basically just very reliable. And so in our role as consulting engineers, we'll work with different utilities and try to help them select the appropriate generation package. And a lot of times the top of everybody's list was brand specific. Maybe they just really had an affinity for a particular manufacturer. My grandfather ran Cat engines and I'm never going to do anything else, or, whatever that preference was. But a lot of times it was the dealer and the support that they had. Their own mechanics were familiar with that particular engine and they just liked working on it and those things. So that tended to be a real high priority. And then load capacity, which was very often done in kind of a crude fashion. What's our peak load? Let's make sure we got the firm capacity to meet a peak load on a cold winter day. And then fuel efficiency was in there, but by and large, a lot of these engines were pretty similar, and there wasn't a huge variation. And interestingly, that dynamic changed pretty quickly over a decade. So you go to 2006, and a lot of places were paying $3 a gallon, and within a short time, a lot were hitting $4 and higher. And so you triple the fuel prices, the dynamic changed. And the technology was changing. Electronic fuel injection came out of the weird R&D stage into a common, taking over the market on newer design engines. And these offered these flatter fuel curves that you heard talk about, and higher efficiency, cleaner burning engines, separately cooled aftercoolers, lowering that turbocharged boost temperature, helped reduce emissions, but it also got a lot more horsepower out of these engines. We'd see the same engine block that used to be rated 300 kW pushing 450 to 500, and some improved fuel efficiency. So there were some great benefits that came along. Well, once fuel efficiency kind of hit the top of the, people started being having less affinity for their particular favorite brand. If their favorite engine was getting 12 kilowatt hours per gallon, somebody made one that got 14 and a half at the same load, they started thinking, I want the fuel efficient engine, And about that time, we started getting better with electronic controls. You know, early days we tried to do in the 90s some automatic demand control where, you know, you'd monitor the load and shift, and things were notoriously unreliable, and very often the operators had ended up just putting it in manual and just picking a big engine and running an overcapacity engine all night because they weren't able to catch the load as it rose in the morning. But mid-2000s, we started getting some more sophisticated PLC-based controls that were actually very reliable, and a lot of people started going to better demand management. And we started looking at things like, is it more efficient to parallel two of the same engines? Because you got this smaller engine, but it's very fuel efficient. So it's purring along at night, right in its sweet spot. The load comes up in the morning, you put a second one on the same one on, run that through the peak of the day, drop it back off at night. And so the way we operated the plants were being tweaked a bit to match the fuel efficiency. Well, the other thing that happened is, you know, Steve and I started working on heat recovery back in 1990, and we just thought it was the greatest thing in the world. You know, reality is diesel heat recovery saves more fuel than all of our other highfalutin schemes if you actually look at the numbers. But it's not very sexy, and so sometimes we'd come to the energy conference, make a heat recovery presentation, and there'd be 7 people there kind of like, yeah, right, you know, what's the deal? Don't we all do this? But, you know, when fuel prices shot through the roof, suddenly the clinic that's paying $4 a gallon is a lot more interested in heat recovery, and so is the school district, and so is the water and the sanitation facilities, and so recovered heat became a big deal. But guess what? These new fuel-efficient engines, especially the ones with separately cooled aftercoolers, they don't produce as much heat. In some cases, you lost, you know, a third or more of the recoverable heat. So now when you're looking at engine selection, you're thinking about fuel efficiency for producing generation, but also heat rates and how much heat can you get. And sometimes, you know, maybe using a marine engine that's 1 or 2% less fuel efficient on the electrical side, but it produces 40% more heat in the big picture is a better solution for the community. We're saving more fuel. So, you know, it became a little bit more complicated, and the bottom line is, you know, we had to start looking at these engine selections from a lot more angles. Well, up to about 2006, we were still, when did we go from Tier 2 to Tier 3? That was 2008? Around 2008, you know, and the EPA was stepping in these tiers. So Tier 1, Scott got an engine that had a 10% penalty in fuel efficiency, but still equally reliable, a great engine. Tier 2, there were a couple engines that were very fuel efficient, still very simple, very reliable. Tier 3 hit and everything changed. So let me just go back here and I'm going to show you just a few numbers because I want to make my point that the fuel efficiency still is the dominant issue. This is a graph a utility was looking at. They were very sold on Caterpillar, and nobody gave me a cat shirt, so I can't promote that brand today. But anyway, so their loads were averaging about 350 kW. So here we have a Cat C15, which was the new Tier 3 engine, and a Cat 3508 older version that they had currently, a newer 3508, and a Cat 3456. Okay, so obviously a huge difference in the fuel economy and the electrical production. But if you run these numbers down, here's what happens over the course of the year. It boils down to 40,000 gallons a year in fuel savings running the more fuel efficient engine. This is for one utility, their prime mover. And at that time, they were paying about $4 a gallon. So it's $160,000 a year. That engine pays for itself in a year. I mean, you buy the engine, you pay the mechanic to install it, even a little bit of engineering, you paid for that engine in 1 year. So even if the engine had some reliability issues, you could darn near pay a mechanic to sit in a chair beside the thing and wipe it with a washcloth every half hour if you needed. You know, I mean, it's like whatever. You know, the fuel cost is so significant that you just can't ignore it. Now, let's look at a smaller engine. This is a common, like a John Deere or maybe a Cummins engine. You got maybe it's a 200 kW engine, average load at 120 kW, getting 12 kilowatt hours per gallon. So you're burning 10 gallons an hour. Figure you're going to get 50,000 years out of that engine, rebuilding it a couple of times, 500,000 gallons. at $4 a gallon, that's $2 million worth of fuel goes through that engine. Now that engine might cost $20,000, $30,000 for the engine itself, okay? 1% efficiency difference in the fuel is the price of that engine over its lifetime. So, you know, the cost of the infrastructure, even the cost of rebuilding, becomes really insignificant compared to, you know, Scott's talking about 10% reduction in fuel. So in this scenario, if you have a 10% penalty because you bought the wrong model year engine, that's $200,000 over the life of that engine. For a small utility, that's a huge amount. Now, here we are, 2014, and these are not the good old days. Things are messy. And when we went to Tier 3 engines, the whole game changed. And they started putting on all kinds of things to meet the interim regulations. Variable vane turbochargers, exhaust gas recirculation, and these things are junk. I mean, they are notoriously problematic. And you take an engine that under a Tier 1 or a Tier 2 configuration might go 20,000 hours with minor repair, it's failing every 4,000 to 5,000 hours. And it's not stuff that your local mechanic can just wrench some parts on. It's stuff that a trained mechanic has to come in with the right software to key in the right codes, to sync up the new replacement piece of equipment to the old one, to troubleshoot all the errors. And suddenly the whole universe changed on reliability. Well, now I come back to something that I took for granted. It's very important that we keep the lights on in rural Alaska 24 hours a day. And when is something like this going to fail? When it's 50 below and nobody wants to fly a plane and no mechanic wants to come in dragging his tools through a dark village with no heat, you know? And so, you know, reliability is now up there, but we can't say I want a reliable engine and I'm just going to ignore EPA, because you might be the next person getting a $200,000 fine. So, you know, other things, fuel efficiency, load capacity, heat recovery, all those are factors. But now we're faced with the issues of, you know, reliability and fuel efficiency at the absolute top of our list. So Steve is going to talk about the regulatory compliance issue, and then we're going to kind of land on some options that we do have, because we've taken the time to look through all the different facets of the regulation and find some solutions that do work for rural Alaska and enable us to have a reliable engine. But let me just say, you know, there was a great question for Scott. Well, couldn't you go to the higher fuel efficiency and then put exhaust after treatment? But a lot of that exhaust after treatment for diesels is in the infantile stage right now, and it's pretty crude. And it's not really designed for part load operation, which we take our diesel engines and we rate them for one thing, but we run them at 50% or lower load a lot of the time. The exhaust stream is cool. So most of these schemes actually require you to burn additional diesel fuel to get the temperature up in the exhaust after treatment to make it actually function. So, you know, this stuff isn't really proven in part load prime power application yet, but I think 10% could be a minimal penalty you pay to burn extra diesel fuel to keep the exhaust treatment up and working like it's supposed to. So, you know, the current technology with exhaust after treatment is, in our opinion, a pretty bad option for prime power in rural Alaska, and Steve's going to take it from there. Oh, I guess maybe before he gets into the regulations. Sorry, I tried to skate on that one. Any questions? Yes.
Can you go back to that little calculation?
Yeah.
I'm looking at Kubota,
Yes.
I think your mic's on, if you could, so everybody else can.
It might not be.
Oh,
Yes.
okay. Back in the early 90s, we were running 50 kW generators. Now, going into Birch Creek after, I was doing something else. I wasn't actually finding out to see what running the power generators were like, although I know what they were built like and running in my former studies in that petroleum tech, like say, studying something in drilling where they have this big 2500 kW to run the drilling rig. But going back to Birch Creek back in, say, 89 on up until 96 when we had to replace those Cummins with John Deere's. I was looking at a calculation like that to see how well we can become more efficient. So we lost our power plant back in 2011. Now to install these Kubotas like that, I see quite an increase in fuel efficiency when I'm looking at a 22 kW Kubota generator.
Yes.
I don't know where these things are made, but I think they're made in Japan or something. But I'm trying to find out to see these replacement generators are gonna help, like say you got 20,000 hours. Previously, I learned that 30,000 hours was the capability of, like say, the John Deere 35s. So I just want to point out to the attendees here that that's what we were going through over there. So when I return back up that way, I think we're running 45 kW Kubotas twins that are still yet to be installed. I just thought that it was pretty amazing change, running these Kubotas. I'm looking at 19, maybe to 22,000 or 22 gallons per day in those things, running like that every day. Just to let you guys know, because a lot of you are in much larger towns and villages, even using something like 120 kWs. But Birch Creek, as you know, some of the smallest communities in the state, and it's quite expensive even from the standpoint of running something like a 22, maybe a 30 kW generator.
Mm-hmm.
I just wanted to get that off my shoulders. I just thought I'd share that with you.
Good. Any other questions? Yes.
So with the advent of Tier 3 units, no, I'm okay. You're seeing so they have turbochargers on them. So I read an article the other day about how they're starting to piggyback kind of sidearm generators on those turbochargers. Have you guys seen that application?
I've seen the literature on it, but those things are so touchy. I wouldn't mess with it on a Tier 3 engine. I mean, factory configured, you're lucky if you can keep that thing running for 5,000 hours without major problems. You start adding stuff like that on it and messing with it, and I don't know what the ramifications are too, because you're changing the control scheme. You may be violating the regulations by modifying it that way. So I'd be wary of that. Any other questions? All right, Steve?
Alrighty. I'm Steve Stassel. I work with Brian Gray with Gray Stassel Engineering, and it's fallen upon me to talk about the emissions, regulations, and rules that apply to uses in rural Alaska engines. Try and not keep this too dry. And really, as Brian had mentioned, we're focusing, we went back one here just a sec. Where do you point it at down there? All right, very well. pretty much the most important things that I think that are involved with engine selections comes down to the reliability, the regulatory fuel efficiency, and of course regulatory compliance. If you don't have a compliant engine, the engine shouldn't be in operation. And based on Scott's story, I think you can agree it's not a good place to find yourself. So this is kind of indicative of what diesel engines looked like prior to the Tier 3. Non-tiered Tier 1, Tier 2 engines, they were relatively simple. Pretty much it was a diesel engine with a turbocharger and an exhaust system up above. Very reliable, low maintenance, and relatively inexpensive to operate. Flash forward to the final Tier 4 requirements of a diesel engine, and you can see those a little more involved here. And it's way more complex, and I don't know this factually, but there could be more sensors associated with the exhaust emissions equipment on a Tier 4 engine than there is on the diesel, the prior 2006 and earlier engine. And so I'll just run through a little bit about what you see here. The things that were added, you have the exhaust gas recirculation coolers, very comparable to what's in a gasoline engine since the 1970s. For some reason, on gas engines, they work really well. On diesel engines, not so well. They plug up constantly, and they're a very frequent maintenance issue. And as far as the, let's see, also here in this particular example, we have duo turbos. So if one isn't good enough for maintenance, now you get to maintain two of them. The first one is a fixed geometry, and then the other one is a variable geometry in order to get the torque and whatnot out of the engine. And then over here, diesel exhaust fluid, it's urea. It's a urea water solution which is injected into the exhaust in order to reduce the NOx emissions through an SCR, or selective catalytic reduction system. And then here we have oxidation catalysts and particulate filters. So an awful lot is in a final Tier 4 engine, and by and large, any diesel engine that is in operation on the road system or a piece of heavy equipment that is being installed 2014, 2015, and after that, this is exactly, well, let me throw in a caveat here. There is, for almost everything I say, there is going to be at least one exception to the rule. So I can't, so I have to be somewhat generic in the things that I say. But by and large, after 2014 and going into 2015, any diesel engine on the road or in a off-road piece of equipment has all of this type of equipment involved in it. Now the upside of it is that it does reduce emissions, and I think everyone will agree clean air is a good thing to have. What this is a chart that shows the various steps starting back in 1996 going all the way up to 2012 to 2015, which is about where we are right now. These were the Tier 1, Tier 2, Tier 3. What happened is when they started these regulations, the technology didn't exist, and so the EPA had to forecast what technology would be available to actually meet the emissions requirements. Well, flash forward from the late 90s to almost the mid-2000s, and the engine manufacturers weren't making it. They weren't going to make the final, they weren't going to get here in the time frame allotted, so they came up with an interim stage called interim Tier 4. And as you can see, each one of these has a reduction in emissions, and predominantly in the engines that are used in rural Alaska, the emissions of primary concern is particulate matter. NOx is not in EPA's terminology, a criterion pollutant of concern, and the reason is that we don't have naturally occurring ozone and the other things that need to occur in the environment to create a smog problem like they do in other places in the continental U.S. So one of the things I want to point out here is that, well, actually two things, I guess, is that, let me go back. Whoops. No, I guess, whoops. Getting ahead of myself here. In order to have the optimum reliability and fuel efficiency and comply with the regulations, what we are looking at is using engines that typically fall in this, they aren't going to be a Tier 4. In fact, the engines that we use in most of our power plants are Tier 3, Tier 2, or older engines, not tiered. And some people may think, well, boy, based on this graph, if I'm using a non-tiered 4 and better, I'm using an engine that's pretty dirty. Well, this is the regulation, not what the actual engine does. And what we have found by getting manufacturers' data that has been published and submitted to the EPA is that many of the earlier tiered engines that are fuel efficient, reliable, even though they don't meet these particular tier requirements, they are very low emitting engines with respect to the particulate matter. And again, the PM is the primary pollutant of concern here in Alaska for rural Alaska power plants. And one other thing, the second point I wanted to make is that as the engines went from this style to this level of complexity, the reliability, and the engines that are used by and large in rural power plants come out of either, they're industrial engines. They come out of on-road on-road, trucks, semis, or some of the larger ones are some of the off-road, larger excavators and dozers and things of that nature. But this is where the technology comes from that is used in a power plant in rural Alaska today. And let's see. What I have here is an example, and it's kind of old data. It dates back to 2006. But what it shows is, and I think this is still pretty well current today, that in rural Alaska, out of all 140 rural Alaska communities, there's roughly 30 million gallons of diesel fuel that is used in comparison to how would I say that? 30 million gallons is used for power generation. So these numbers are, let me actually read what it says here. Okay, in 2006, roughly 30 million gallons of diesel fuel was used in PCE communities. The largest 9 hubs, the ones that usually are Title V and have the higher air quality emissions regulations, used pretty close to half of it. So what that means is there's roughly 15 million gallons of diesel fuel that's being used in 140 power plants around rural Alaska. And the point of this is that there's not a very large density of fuel burning diesels in the 140 communities in a large geographic area. And in comparison, so all of rural Alaska between power generation and the roughly 30 million gallons of fuel that's being used for heating and the little bit for off-road equipment, dozers, graders, and things of that nature, is a very small fraction of the 565 million gallons of fuel that are used in the state of Alaska. So the point in all of this is that it's important to have a pretty clean diesel running engine, but there is so few diesels that are operating in rural communities that they don't necessarily need to be as clean as what we're seeing here. And again, the purpose of these final Tier 4 requirements is that in the continental U.S. and other places, Canada and Europe, and even here in Anchorage, there are, I don't know, tens of thousands, hundreds of thousands, millions of operating diesel engines. So it's really, really important to have a really, really clean engine because there are so many of them. Well, in rural Alaska, I know in many communities, the only diesel engine running is the power plant unless somebody's clearing the snow off the airstrip. So a very low density. And I guess just for comparison, I looked this up today. In 2012, according to the EPA, 60 billion gallons of diesel fuel were consumed in the U.S., and that was for everything. And of that, 36 billion gallons was for on-highway trucks. So a little more than half of it. And again, the technology that I showed you in that second 2014 final Tier 4 engine, the reason they're having to get it so clean is because 36 billion gallons of fuel are going through them. So it needs to be a very low emitting engine in order to keep the pollution down. So what I'm showing here, I have 2 different examples of, this is a cat. We have some 35. In fact, this, I believe this is the data for Scott's engine, the one that they had to reflash to Tier 1 and they now have in a standby configuration. And what I'm showing you here is that this is what the regulation is for a non-tiered engine. This is, it's an API standard. And this is what the final Tier 4 requirement is here. So you can see it's a really huge reduction in emissions of particulate matter, which is a good thing. But the engines that have been in use in rural Alaska, and this is the larger CATs, are relatively low-emitting particulate matter engines. And the reason this occurs, I think Scott had mentioned the term low BSFC, brake-specific fuel capacity or consumption. In simple terms, when an engine is tuned in order to maximize the fuel economy, they say that's a low BSFC configuration. And that inherently, because of the fuel being burnt efficiently and getting the most amount of energy out of it, it puts out the least amount of particulate matter and without, in the absence of having all the exhaust equipment that I showed you on the Tier 4 engine. And this here is some information on the Series 60 engine. AVIC has 30 or 40 of them in use, I think. Relatively, 2000, maybe to 2006 model years, so fairly old stuff. But you can see here that, compared to the, let's see, here's the Tier 0 requirement, which is green. The Tier 3 is this line here. And again, Tier 3 didn't come into play until 2006, 2008. And yet these engines, because they are designed and programmed to be the most fuel efficient, are operating at relatively low particulate matters emissions. And again, what we're looking at is selecting engines that have, they have to be regulatory compliant. In this case, they are fairly low emitters of particulate matter, and equally important, they are exceptionally reliable and they have very good fuel economy. Whoops, what happened there? All right, so now I'm going to talk just for a moment about the different rules. Some people had asked about what is the status and of the rules of emission in Alaska. And fortunately, now that we're in year 2014 on the way to 2015, things are becoming a little more steady state. Over the last 4 or 5 years, they were constantly changing, but things have somewhat leveled out. And so in very general terms, there's 2 different emissions rules. One is called Rice-Neshap. It applies to engines that are April 1, 2006 and older. And if engines are newer than April 1, 2006, which Scott ordered one prior to that date but got it after, falls under the New Source Performance Standards requirements. And so the key difference in that is that under NSPS, the burden of emissions compliance goes to the manufacturer. And a couple things came out of that. One is you can see all the equipment that went onto the engines. They put all the oxidation catalysts, particulate filters, SCR, diesel exhaust fluid, a fair amount of complexity. But they're what are called or classified a controlled emissions solution. So the onboard engine is not only controlling the diesel engine, the firing of the fuel, the timing of the engine, all those things, but it's also monitoring all the other parameters, the temperatures, the pressures, the particulate matter, everything, and it's constantly changing in order to optimize the fuel economy and stay within the emissions requirements that they're set by the EPA. One of the outcomes of that is the engines are not maintainable by anyone other than a technician that's certified with the computer equipment. So when an oxidation catalyst or something with the urea goes wrong, the engine will get shut down, which is not a good thing for prime power plant. And in order to fix it, even though a mechanic could physically replace the item, in order to start up the engine, to enable it and authorize it to run, somebody has to go out there with the appropriate software, plug it into the computer or into the engine, and authorize the engine so that it'll operate. And the reason that that level of control is put on it again is that the emissions requirements under NSPS, the burden is upon the manufacturer. So what better way to control and be able to meet your emissions requirements than have your technicians do it themselves? Not a very good solution for rural Alaska because it is really, really expensive to get people out there to do anything. Under Rice-Neshap, and again, these are the prior to 2006 April engines, the responsibility falls under the owner and operator. When the rule, all right. When this rule first came out, and it was, I think, in 2010, there was quite a bit of burden placed on all operators of Rice-Neshap engines, continental U.S. and in Alaska. And the state of Alaska submitted what was called an alternative implementation plan to the EPA. And a lot of things came out of it or were involved in doing it. But the bottom line, what came out of it was that for an engine which is Rice-Neshap, which is older than April 1, 2006, in order to be compliant with the EPA's requirements, it's fairly simple. You need to change the oil every 1,000 hours, and if you have an engine that's operating hours, and you know, so for the bigger engines, it's what, 150 gallons or something on your I mean, it's a lot. Yeah, we're talking around 200 gallons. Okay, and at $6 or $8 a gallon, you're talking pretty significant dollars to change out that oil. $20. $20? All right. Ouch. He said it was $20 a gallon, 200 gallons. That's $4,000 for an oil change. And so it's pretty doggone expensive to change your oil every 1,000 hours. If you operate the unit continuously, that's 8 times a year. That's $32,000. Well, the EPA recognized that there is another way of being able to determine if the oil can continue beyond that. So they do allow an oil analysis plan, probably something not done too frequently by smaller utilities with smaller engines and lube capacities, but they do provide that caveat. You have to inspect the air cleaners and the hoses, and this is really the most important part of the whole thing. You have to document it. When a regulator comes to your utility and they ask for you to show them how you're complying, if it's not written down, it doesn't matter what you've done. It doesn't count, kind of like the IRS, right? If you don't document it, it never occurred. and I don't know what happens then. So the upside is that AEA and AvTech, through their operating training program, they do have CDs and things that you can get online that have examples of maintenance logs. And it's not really difficult to be able to document this type of information. You just need to do it in an appropriate manner, and probably in addition to written logs about what was done to the engine, it's a good idea to hang on to your receipts and things. And by and large, what in my limited personal experience, when an EPA person shows up to look at something, if you can show them the correct documentation and they look at it, it's like, yeah, that's what I need, then they're satisfied. If they look at it and it doesn't answer what they're looking for, then it raises red flags, and they go back to the office and start sending letters, and it's a lot of work. Wow, okay. So under new source performance standards, and again, these are engines that are April 1, 2006 and later. They're the tiered engines by and large. Similar circumstance to Rice-Neshap. The EPA recognized that Alaska is a little different, and it doesn't make sense to put the same burden on rural communities for a lot of reasons as it does in the continental U.S. And I think the primary reason is that if you don't have a lot of emissions emitters, meaning not very many diesel engines, then you don't need to have quite as strict of a requirement as you do in the continental U.S. Plus the cost of maintenance is just astronomical. So what came out of the new source performance standards and the state of Alaska's involvement is that they eliminated, the EPA, I said earlier, they acknowledged that NOx is not a criteria pollutant of concern. That's a pretty big thing, I think, getting a EPA to acknowledge that they're not concerned about a pollutant. But they limited it to rural Alaska. So they said that, no, you don't need to use SCR. And again, SCR is a selective catalytic reduction thing. It reduces NOx, and the way it's accomplished is you inject the diesel exhaust fluid into the exhaust system, and it consumes it and oxidizes it and changes it into nitrogen and water, I guess. And that's a nice thing, but there are no Tier 4 engines that can be purchased on the market where the manufacturer will allow you to remove that component. And again, the reason is they're on the hook for meeting the emissions requirements. They spent millions of dollars, many millions of dollars, in order to come up with the technology, test it, get it approved. And the market of Alaska, for the number of diesel engines that are used in the 140 communities, no way, you know. So what happened is by not requiring SCR, that means that a final Tier 4 engine, by and large, cannot be used in rural Alaska because there isn't the infrastructure for it. You know, there's no urea, there's no diesel exhaust fluid, there's not the infrastructure for moving it. So there were some unintended consequences that came out of that. The other thing that they did, which is really good, and this is specific to rural Alaska and doesn't exist anywhere else in the United States, they do allow the blending of used oil, and that's really important because used oil, if it doesn't get burnt in the engine, it generally gets dumped on the ground somewhere. So it reduces the pollution of the environment, and it also, there's a lot of BTUs in the oil, and it displaces the diesel fuel, so it's a very positive thing. The other thing they did was they exempted the pre-2014 model year, which is where we are right now. We're now in 2014 model year engines and probably very close to 2015. They said you don't need to use ULSD in those. And they allowed the use of engines certified to marine engine standards and Tier 3 non-road industrial engine standards. So what does that mean? Well, the engines that go into marine vessels have, and I guess we really didn't talk much about marine engines specifically, did we? Well, a marine engine is an industrial engine by and large, but they put a water-cooled manifold on it, and they put a water-cooled turbocharger on it. It reduces the temperature of the ambient, and it's a fire safety hazard for below-deck spaces on boats. The upside of it for rural Alaska is it gets a lot of the heat that normally would go up the exhaust stack into the jacket water, and it's very easy then to recover it for heat recovery. And in real simple numbers, a Tier 3 separately cooled aftercool engine, which rejects about a third of its heat to an aftercooler, the heat to the jacket water is 1,500 BTUs per kW of load. That's a real generic number. A standard industrial engine that has a common circuited or a single circuit jacket water and aftercooler where all that heat goes to the jacket water radiators is about 2,000 to 2,200 BTUs per kilowatt of load. And then if you have the same engine that is marinized or has a marine manifold or a wet turbo, it bumps that up into at least 3,000 BTUs, and in some of the smaller engines up to 4,000 BTUs per kW of load. And so that's a really important thing, as Brian had talked about. You know, in selecting a diesel engine, especially if you have a water plant, a washateria, some other community buildings really nearby, to be able to get that additional heat out of the jacket water and save the heating fuel, it really makes a big difference to a community. So, regarding the Tier 3 non-road industrial engine, this is what the EPA decided would be the standard for rural Alaska, because Tier 4 engines won't work. You know, there is no diesel exhaust fuel fluid. And what a Tier 3 is, well, what it is now, a Tier 3 engine up until 2 years ago was the prime mover and what was being sold for off-highway and on-road equipment. And so they was very fuel efficient, but it had all the bells and whistles that we don't like, variable geometry turbochargers, exhaust gas recirculation, and other things that haven't proved to be very reliable or effective in bush Alaska. So as of this year recently, this model year and in the future, final Tier 4 engines are the only thing that can be used for mobile equipment anywhere in the United States, and Tier 3 engines now have been relegated for emergency or backup power. An emergency engine or diesel, like in a building like this or in downtown Anchorage or anywhere else, it may operate a few hours a year. So fuel economy, nobody cares. And in the market of the Tier 3 engines now, because nobody's driving them on the highways and fuel economy isn't important, it's how cheap can you sell the thing in order to get it into the building. Well, those kind of engines, the fuel economy of these Tier 3 engines that are now classified as non-road industrial but are really emergency or backup, that's their purpose and their market, the fuel economy is horrendous. And so the examples that Brian showed you, it's even worse. So a Tier 3 engine is no longer a viable solution for rural Alaska. Whoops, plus I had one other thing there. Right now, if you use either a 2014 marine engine or a Tier 3 2014 engine, it requires an after-treatment particulate filter. It's a third-party solution which requires, engineering and design. And although they've been used on vehicles and buses and whatnot, there is no proven track record of reliability for use in an Arctic environment such as rural Alaska. So what are the options? You can purchase a 2014 final Tier 4 engine, but if you're in rural Alaska, I don't know how the heck you're going to operate it because you don't have the diesel exhaust fluid available to make it run, and the cost of maintaining it is going to be an extreme burden to the utility. You can purchase the Tier 3 industrial engines that I mentioned, but then again, you have to put a particulate filter into it. You can do the same thing with the 2014 Tier 3 marine engines, but also as of this year and in the future, you need to do the particulate filter. And again, the issues with the filters, which I kind of hit on, is that they're not OEM, they're not equipment that's provided by the original equipment manufacturer. It's not a designed and controlled and integrated system. It's something that's put on aftermarket. And there's a lot of manufacturers that do this, and the main market is somewhere in the continental United States. Not in rural Alaska. They're fairly expensive. They add cost. They do not reduce fuel efficiency. I mean, they do not improve fuel efficiency. There's more maintenance, and we're uncertain of the reliability. I recently, talking to a particulate filter manufacturer, asked him 3 questions. I said, does your filter improve fuel economy? The answer was no. Does it improve the operation of the equipment? The answer was no. And does it improve or decrease maintenance requirements? And the answer was no. And my question was, well, why would we consider putting it on an engine in rural Alaska? We want it to be reliable, we want it to be fuel efficient, and it needs to meet the emissions regulations. So, a solution. The Alaska Energy Authority, Great Stassel Engineering, and other firms have been using what we call, it's used inventory. Aged inventory, I think, is what somebody once called it. And what it means is that it's stuff that's been around for a while and is either used for a little bit or it hasn't yet gone out, but it's an older piece of equipment. Pretty much, we've used all those up. We can't find them anymore. So you can use, if you can find one, you could use a brand new 2013 engine, prior to 2014, anything older that's brand new, but they're hard to come by, and it would meet the emissions requirements. You can use a low-hour used or rebuilt engines. We've done a lot of that. Some of the Series 60s engines, the Cat 3456 is something that we use a lot of because they're very low particulate matter emissions, exceedingly good fuel economy, reliability. There have been issues that we're continually addressing. Or you can use remanufactured engines. And this is something that, it was only about 6 months ago, I think, that we really started to realize what a remanufactured engine was and how it could come into play to providing at least a near-term solution for engines for rural Alaska. And that issue here is, again, the new engines, the new 2014 engines are all designed they're equipped with all of that stuff on the exhaust. And there's no way of removing some component of it, and they just won't work in rural Alaska for the reasons that we discussed here. And so, what do people do when all the the relatively unused or new unused engines are gone, and you don't want to rebuild an engine? Well, the option is to do a remanufactured engine. And this little note here, we just throw it out there. It's not the same as an OEM repower program. What that means is if you a utility were to call up a local vendor and say, I want to get a remanufactured engine, well, probably 95% of the engines that they deal with are for mobile sources. And unless the person you talk to really understands what the requirements are for stationary sources and the regulatory relief specific to rural Alaska, it's not unlikely that they're going to say, oh, we can give you an OEM repower, and that only is allowable for mobile source engines. And it's really pretty cool. The EPA realized that, there's a lot of stuff out there that people need an engine to make it work, and all that stuff, the exhaust emissions equipment, won't fit in the truck. And so there's a limited number of engines that the manufacturers can literally take with a brand new block and make a brand new engine, but certify it to an older emissions limit. Okay, that's called an OEM repower. It is only available for the on-road or for mobile sources. It is not applicable or eligible for a stationary source. And in fact, if somebody were to get one of those engines inadvertently and rebuild it and repurpose it for a stationary source, you would immediately be out of compliance. So an OEM repower is not the same thing as a reman. So in order to make this work, the blocks need to be prior to 2014, and there are hundreds of thousands of used diesel blocks of all different size, shapes, configurations that are available. It's just a matter of finding the right one that for your particular application, and then remanufacturing it to a standard that the EPA recognizes. There's some issues here about the cost. You can't spend more than either 50 or 75% on the remanufacture of this engine, and if you do, then if you hit the 75%, the EPA says, okay, there's so much work has been done on this engine, we're going to give you a new born-on date. Well, the born-on date is the date they finished the work. Well, it's now 2014. The only way that engine could meet the requirements is to have all the exhaust emissions equipment that I showed you on the final Tier 4. So you have to know a few things about what's going on here, but based on our preliminary investigations, we can, there is probably nearly an unlimited, as far as the number of engines needed for rural Alaska in the near term, an unlimited number of diesel engines that are eligible for remanufacture, that the cost of doing that, and what you end up with when an engine is remanufactured is the equivalent of a used 0-hour engine. So it's not brand new, but everything that's gone back into it has been retooled, reshaped, reconfigured. It's a like new 0-hour engine, it just is an old block. And in doing that, we found some circumstances that certain engines we can, it makes sense to take a block and upgrade it from a Tier 2 to a Tier 3 in some cases, on the Marine specifically, because we get better fuel economy and some other things. So there's some things that can be done within the regulation. But in broad terms, in order to get a remanufactured I think, don't quote me on this, but a Series 60, roughly 200 kW engine, to have it remanufactured to be a Tier 0 or a Tier 1 engine, which is like a 2000, 2002 type of a block, exceedingly good fuel economy, very, PM emissions nearly what the final Tier 4 requirement is. Extremely robust and reliable. The cost of that's about $45,000. Whereas the cost of doing a final Tier 4 engine that would be the equivalent is in excess of $100,000. So what we have found so far is that the applicability of remanufactured engines for applications in rural Alaska is going to provide, at least in the near term, a source of blocks and engines that meet the fuel economy requirements that we're looking for, that are reliable, and most importantly, that comply with the emissions requirements of the EPA. So what's next? The Energy Authority is in the process of writing up some guidelines of how to weed your way through these requirements to make sure that when an engine is being ordered, it meets the requirements. The state of Alaska, from my understanding, both the Energy Authority and excuse me, DEC are continuing to work with the EPA to try and find additional regulatory relief for rural areas of Alaska. So that's it. Any questions? All right. Yes?
Mark Hoffman with Power. It would seem to me that, I mean, our premise has been the best way to get more out of a diesel engine is to run it differently than what has happened for the last 60 years in primary power, or 80 years, which is allow the engine to run through its full RPM range. That's what makes it more efficient. The problem with primary power, when you're stuck at 1800 or 1200 RPMs, you're not being able to take advantage of the full fuel efficiency map of the engine. So when we do that, we, as an example, average about 211 grams per kilowatt hour, and even at 10% load, get only as high as 250, and at 20%, we're about 230. The question I have is, we're familiar with the challenges of Alaska. I think they're very serious ones. We understand the issues. But as a technology company trying to create a product that can help Alaska, the question I have is, when what we end up competing with is this remanufacture strategy, because we can in fact beat the fuel consumption of any engine ever built that's fixed speed, and we can meet all of the latest emissions requirements, but obviously the cost of goods up front is certainly going to always be higher than if somebody wants to keep going out and remanufacturing whatever engine box they can find. So again, my question is, you mentioned maybe this is a short, medium-range solution. Could you talk more about that? Because frankly, it discourages OEMs like us to want to invest in how we can give you a product that can work not just now, but 20 years from now.
So I'm not sure I got the question.
Well, the question
why is this a short-term solution? Or
Yeah,
solution?
exactly, because for me, I'm going to be competing with remanufactured engines, and the question is, why am I going to invest? I have a 600 kW system today that's going to be Tier 4 compliant with better fuel efficiency. Why would I want to invest in a 100 or 200 kilowatt system, which I know is very commonly needed in Alaska, if I'm going to compete with a 40,000 remanufacturer? So how long is this thing going to go on with remanufacturing?
I can't answer that one. Yeah. No, when I say near term, I mean is the state of Alaska is looking at working with the EPA to find out different solutions. Until different solutions have been found, I think the remanufactured engine process and reuse of existing aged inventory is going to be the answer, at least for remote areas of Alaska. The oil.
One in there. When somebody can demonstrate in prime power variable load application that an engine with all this garbage attached to it can run for 5,000 hours without a major failure that requires a highly specialized mechanic to come to the village to do it, then they might be viable. But right now that isn't an option. So, and when we can get an engine that doesn't require urea, because we have enough trouble safely handling diesel fuel, do we want to really be dealing with ammonia? Storage and transportation. So those are technology issues that have not been conquered yet. And our opinion is we'd rather see somebody conquer those issues where they're on the road system and have access to good technology and technical support, not out there where it's a life and death issue when the plant goes offline at 2 in the morning and 60 below.
And that's the only time the plant goes off.
Absolutely.
Now, we understand the issues. Numbers on fully are not good. Tier 2.
So, another question here?
Yes, thanks.
Go ahead.
Man, I learned a lot about engines. Thank you. Really appreciate it. You flipped backwards, and I love that because you're closer to the slide I wanted to review. So if you could forward up a slide or two.
What are we looking for here?
Those right there.
Okay.
Bang. Okay. So I was curious about the Ukraine, Europe, Mexico, China. What do their tier 2, 3, 4 standards look like?
NS 40 CFR, let's see, 40 CFR 60 could probably fill this room with pages of all the air quality rules. I mean, it goes to, Quad Z is Rice Nishap. That's what, 4 times 28? There's 28 letters in the alphabet. And there's something down in the 5Y. The only thing I focus on these rules is a very, 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 very infinitesimally minute portion of the rule that's applicable to remote areas of Alaska.
Gotcha.
So there is 99+%, I don't have any idea about.
Then the next slide, just to tack on one more after that, that one.
Okay.
So our engines were way below, say, the tier 0, I mean, we were performing, say, at 100.
You're saying some of being used. And again,
Yeah.
the reason this is that this is, when the EPA started out with rules, they had to start with something.
Of course,
And they
yeah.
took the dirtiest engines. Well,
Yep.
but when these are like a tier 0 to tier 2 is, I think, pretty much 2000 to 2006. Well, that was when the high-pressure rail systems, electronic fuel injection, variable timing, all came out, which is pretty doggone good. Hundreds of millions of hours of proven performance. And they're tuned for the best fuel efficiency, which gives low particulate emissions.
Absolutely. So again, compared to the rest of the world, I mean, that has got to be better than everybody else. Or if you go back to our original engine.
Oh, absolutely.
I mean, is Cat and John
Yeah.
Deere selling those original
Right.
engines all across the world?
Right.
They're still making them, right? Or
Europe standards are very comparable to the United States. Canada, Europe, and the U.S. are very comparable. I know very little about the Marine, but the Marine standards, they aren't quite as tight as oops. Guess I got to point to the right thing. I mean, the Marine standards are somewhere in this range here, but those Marine standards are worldwide as well. So the by and large is that, I mean, there are, what did I say, 60 billion gallons of diesel fuel in the U.S., roughly 60% of that is in on-highway rigs. So it's pretty doggone important to make them clean. But yeah, lots of places. Mexico and third world countries, that's where the engines that can't be sold in rural Alaska end up going because they have less strict emissions requirements. Any other questions?
It's almost lunchtime.
It is lunchtime. Thanks.
That's it.